I'm going to give a short presentation about how to debug routing loops in your implementation, which is as hard as finding the buffer bloat stuff. And it's starting with a little anecdote. Like in summer 2009, Xavier, can you whistle again so we get a little bit more? Hey guys, we're talking here. So in late 2009, two guys showed up on our mailing list, so on our Batman mailing list, and said, hey, we ran a couple of tests on certain grids and certain scenarios, and under these and these conditions, your routing protocol implementation loops, but we don't know why. It turned out to be a grid like 8 nodes in a row times 8 nodes, so 64 nodes, and I would just turn off one, and then in another corner of the network it would loop. How do we debug this? I said, well, we have a debug mode. I think every routing daemon has a debug mode. Give us all the logs. We debug it then. As you can imagine, as there are 8 nodes times 8 nodes, there were a lot of logs. And I was like, okay, now we have the logs, but how are we going to debug a mesh of this size, doing some crazy stuff somewhere, and then some other crazy stuff is happening somewhere else? How are we going to find this routing loop? And fortunately, they managed to further get the problem to a smaller size. Their testbed looked like this. So they reduced it to 10 nodes that would have a very good connection between them and some weaker links around. And then they would turn off one node in the middle, and it would loop on the outer side of the mesh. Only for a short while, but it loops. We had packet loss, and we don't like loops, we don't want loops. But how to find this loop? And actually it started when in a discussion and some thinking, and we have all these logs, and wouldn't it be nice if we just would visualize what all this data that we have accumulated, is trying to tell us in an easy manner. So at that point we thought, okay, the Batman protocol is very similar to a traditional distance vector protocol. So each node only has the information about its direct neighbors. So how are you going to relate something that's happening in this end to something that's happening on the other end of the network? So the idea was to write a new tool, which I called Bisect, which would read all the logs from all the nodes into an own internal database and link all the routing information internally together. Because Batman only does one thing after the other, so there must be an event, and this database reads all the logs one by one and chains all these events together into one big event database. Now that we have this database, we can do all kind of funny things on this database. So I'm going to show it. That's easier. So we have Bisect, which is part of the BAT control, a BAT-CTL tool that comes along with Batman Advanced. And we give it all our logs. And in the default mode, Bisect will go through the entire database for every routing change, and will go through all the routes and check if there are routing loops. So it will look for us if in the logs are routing loops somewhere. So I just run the command. It parsed the database. These are 1 million entries that it just parsed of log and routing entry changes. And we can see here host 4 in our environment has, after certain sequence numbers, routes to certain other hosts. And here we have longer routes. We remember it's the same topology that I showed earlier. And we can go up a little bit and we see here Bisect was able to find a route that loops. Okay, yeah?
Just to clarify, is that logged from a single node or is that the logs from
all the nodes?
Okay.
So the database is the whole view of the network, and the algorithm goes through the whole network, checking all the routes.
So you have timestamps to correlate the...
No, we have no timestamps. It's all based on the sequence numbers that we get from the network that link the information together. And to show you the other nice features we have, I had a special note. I looked it up before. I cheated a little bit. So we have host 8 that shows a routing loop here at sequence number 69. There would be a routing loop between host 9 and host 8. Now it would be nice, you know, what was the routing table at that point? So we can go back to Bisect. I admit I prepared it in advance. You know, live demonstrations are somewhat painful. Let me see now. So here we have the routing table of host. It's on top. So we have the routing table of host 8 here at sequence number 68 coming from host 2, and that's how the routing table looks like. So we get to host 5, we are host, so here we see we go to host 5, we are host 7, host 9 is a one-hop neighbor, and effectively we just changed the route towards host 9, which creates the routing loop that we saw in the check earlier. Now, to fix we see the routing loop, we see the routing table. Now we want to know, why is this loop happening? So for Batman, it's essential to see how did the OGM travel through the network and what did it do so that the routing loop occurs. So we come to the final mode that Bisect offers, which is a visualization of the sequence number traveling through the network. So here we see the sequence numbers, the OGM started at host 2, and it flows to host 3, which is then rebroadcasted to host 2, and so on, to other nodes, and we see how the TQ value, which is our metric, changes, how the TTL changes, and we see in effect here the TQ goes up at a certain point, which should never happen, but it happens due to a bug in the implementation, and that's what caused the routing loop. I know I didn't say everything. It is a brief overview. It's a lightning talk. Feel free to ask more.
Can you remind us what the TQ is?
TQ is the metric that we sent. It's a value. It's just the percent value of the packet loss for each link.
Okay.
That's supposed to go down with each hop.
What's down?
Down. So the reduced. It is the packet loss, or the packet loss goes up, or the link quality goes down.
No, the value should go down.
Yes. And here, due to a bug, the TQ went up, which caused the routing loop. Okay, that's...
It's not monotonic anymore.
Yes, it's not monotonic anymore. Okay, thanks for listening, and the next speaker can come and give his presentation.
What was actually the bug then? What was actually the bug then? The implementation of it?
Let's discuss this. Then we have to dive into the routing protocol.
Okay, it's complicated.
It's complicated.
It's not an integer wrapper or something.
No, that would I find more easily. Yeah. No, the
Hope this works.
I hope so too.
Okay. Good. Maybe some people have noticed the OLSR.org team did not bring any new generation code with them. We are here with the same stable code base as before. But I've done some other stuff partly for the OLSR project. I called, after starting it sometime, the OLSR cleanup project. It's just a little bit working. You know, when you have a code base, it doesn't matter how good it was a few years ago. When you start patching it, improving it, after some time it gets a total mess. And then when it gets too worse, you have to work on it and clean it up again. So I've divided this in in a few areas. One is API namespace. We have a lot of strange functions in OLSR.org, and nobody knows why they are called as they are called. The scheduler, more likely the schedulers, because we have two of them. The commons, that's the source common directory of stuff. There are some easy to use APIs that help us for some small problems. The dependencies, we have different parts in a routing protocol, and they partly depends on each other. And in the stable branch, most likely when you try to take one part and say, I want to use this, you get the rest of the routing agent hanging as dependencies on this part. And finally, the configuration system. Let's look at the namespace cleanup. Let's do a small quiz. Does any one of you know what the first two functions do, and have a guess where you will find it in a routing agent? Any idea what is add PTF or register PCF?
Pointer to function.
What?
Add pointer to function.
No, unfortunately not. I must admit, when I first saw this, I saw it, I think, in the security plug in the first one. I looked at it and said, okay, I have no clue what this function is doing. And it turns out it's the add packet transformation function. So it allows you to do stuff with packages before they are passed. And I think register PCF is something, an old event system of the OLSR, and you will be informed about changes of neighborhood topology, and the parameters are just 3 integers. And then we have things like this, OLSR alloc cookie and OLSR cookie malloc. I can tell you it's confusing as hell when you are used to automatic function name generation. You just type a few characters and say, okay, replace this, and most times you have the wrong one because they have really crazy names. Scheduler cleanup. We have a memory and a timer scheduler, and they were tightly interconnected in one file. So some time ago I started and say, okay, we have to split this up. We want to have memory. We want to have memory cookies and timer cookies. And we have this socket scheduler and timer scheduler thing that don't really have that much to do. So we want to split this up too. And in this process, I noticed there are some API codes missing. So you can register a timer with our timer scheduler. You cannot get rid of it anymore. You have to. There's no API call to remove the registration.
Maybe you want to also add the story about the timer going backwards.
I will see if I have time for this. What is our commons? It's just our source common directory. And I've done some cleanup there too. For example, I moved our handling of IP addresses and future MAC addresses to this, so we have an easy small API to handle conversion between strings and binary representations, handling prefixes, handling different kind of addresses in the same object. You can compare them, and you don't need to care about what's really going on. You have some checks on the string. I've added, especially in this area, lots of Doxygen comments. Most of the stuff was not commented at all. So I plan to do some README, and there are already some automatic tests for this. There's a small independent repository called comments.git on our web page. And so you can say, okay, I've done some changes here. Please run the automatic tests again. Let's see if at least the tests are still working. Dependencies, yeah. My idea was maybe a little, not just related to OS.org. We have lots of nice building blocks for building network software, and it would be good to be able to use them without the rest of a routing protocol, because maybe I want to write something else that is working on networks, but I don't want to do this again. So what's the current status? You can use the logging without anything else. You can use our memory management. You just need the logging. You can use a circular clock management. I will come to this if I have enough time later. And it's only depending on memory handling and the logging. And you can use the socket scheduler and the timer scheduler apart from each other. You just need the stuff above it. So with these building blocks, it's much, much easier to build up network applications in C, because you already have to have these APIs to do it and don't need to reinvent the wheel the 10,000 times. On my to-do list is our plugin system, which must be pretty high in this list because we are doing lots of stuff in the master branch and plugins, and so they must be initialized pretty early to put much of the put stuff we use later in the plugins. The configuration system, at the moment the stable branch use Flex and Bison, and I'm not sure if anyone has ever enjoyed using Flex and Bison, but it's a pain in the ass. It's buggy as hell, I think, the resulting code, and it has memory leaks we were never able to track down, because it's lots and lots of automatic generated code. It's hundreds of kilobytes, and you look at it and say, no, I can't comprehend what this thing is doing, I just have to believe it works.
But it's just a single memory allocation.
Yes, yes, we had some months ago we had a thread on our mailing list. Some people were saying, okay, we're using your current stable OLSR and it has a huge memory leak, hundreds of megabytes within a few hours. And we said, okay, that's not possible because our typical hardware doesn't have hundreds of megabytes and it's run longer than a few hours. And they were discussing back and forth, and finally, after some time, we discovered, oh, someone is experimenting with dynamic configuration changes and just running our configuration parser again and again and again and again. And of course, there were every first times. Normally, it's a constant loss of memory, and in this case, it was a lot more. Too, so you can have your own telnet console in the software without needing to implement this stuff. Configuration cleanup. Yeah, we have this FlexBison horror. We have some self-written stuff in the master branch, which is not really that good too. The problem is we have different configuration formats. The one we use for all at the moment, we have this UCI stuff in OpenWRT. Some people are saying if you don't use XML, you do it wrong. I don't agree with that, I must admit. We have stuff that we want to read configuration maybe from different sources. We want to read it from a file, from an HTTP server, maybe over a socket or directly from an SQL database or LDAP source. We would like in the future to have changes of configuration during the runtime without starting the whole routing daemon again. And we would like to have some independent validation of configuration parameters before we read them into our binary databases. So I have started a new API that can do all of this. Some people I've showed the API say it's a little bit over-engineered at some points, but I think it will do fine, and it's totally independent from the OSR code base except the OSR comments. So I'm using our linked list, our AVL trees, and some string manipulation, and the the new IP and net stuff. You can easily have, with this API, you can have multiple instances of configuration databases. You can define something called a configuration schema, where you define how your configuration options look like and what are the checkers, what are the formats you want to do. There are some pre-made checkers, you can easily define your own, which just tell the configuration parser, yes, this is working good, or no, because of this reason you cannot have this configuration parameter. When you do this, you have a reader and writer faculty that can read different kinds of sources, and then either parse the stuff itself or just give it over to a configuration parser, which implements the format. So you can have independent modules saying you have a file module that just reads and writes files, but doesn't implement any configuration option itself, but just give it over to a different system. And we have something called delta management. You just take two configuration databases and can register a bunch of callbacks, and then it calculates the differences from one of the databases towards the other and calls the callbacks and say, okay, this section was added, this section was removed, these entries were changed, and so it's much easier to handle configuration changes on the fly. Even be able to listen to configuration changes done for other parts of the program. Just add another callback in your plugin and say, hey, I'm interested in this special configuration option of the master call. So this is basically the building blocks of this API. I've already said the database schema. The IO handlers are what I call what loads or saves the data. Some of them, like LDAP or MySQL, most likely will pass the data itself. Others just add the data to a binary buffer and then give it over to the parsers. The idea is that we want to have the same configuration definitions for the core and for the plugins. At the moment we have some different stuff, and I want it to be totally independent from everything else except OSR comments. The status of this whole project is the schedulers cleanup is done. It was merged yesterday back into the master branch. So you will not anymore find a scheduler.c, but you will find a file what is a clock.c, or is a timer.c, and what is a sockets.c. The commons cleanup is, I would say, nearly done. There's still some testing missing and some, I think, a little bit commons, but mostly it's done. The configuration cleanup, the API is working. I still have to do some API testing. And this IP dependencies, like I said, a few building blocks are already pretty easy to get out. The rest of this stuff will follow later, I hope. So Aaron told me I should mention something about this strange thing called circular timing management. What is us insane enough? Do I have the time?
1 minute.
Okay. What is us insane enough to have its own internal timing representation in a 32-bit integer in milliseconds? The problem with 32-bit and milliseconds is it loops over every 40 days. And we had problems with this. You have even more problems when some Xen virtual machines decide, oh, time jumps backward for 1 hour suddenly. We had a time change and suddenly your timers don't fire for 1 hour. The routing protocol just stops for 1 hour and then starts again, and nobody's knowing what's going on because it happens only 1 time every year.
Is it well known?
No, in the other time you jump forward, so all timers fired at once. So OSR has something like a circular time space and since this is managed itself, and when the system time jumps forward more than, I think, 60 seconds, it just assumes a millisecond has over and just continue forward.
So you're not using the its monotonic clock, you're using the real time for time?
Yes, because we had some problems with this too, because BSD, Linux and Windows are slightly different in implementation this, and so we said we'll just get time of day and do stuff ourselves. Good.
It works brilliantly.
So it's a pretty boring work because the user most likely will never manage to see what's going on except the configuration system. But I think it's really important to do this from time to time to your projects. Looking again at the API you have written, what are the names of the functions, how you sorted them in different files, and cleaning up. If you don't do this for years, then you get a huge mess and a lot of work to redo this. Thank you.
I got a video of it. I will show you guys. I'll just show you once. Okay, hello everybody. My name is Amir. I'll be presenting a tool called Mesh Tool, which is basically a mesh network administration slash research tool that I've been working on. So just a bit of background, the tool started as a Google Summer of Code project back in 2009. It basically took the FryMap application and adapted it to the Eclipse IDE platform, and later on it basically continued on its own path. Okay, so what is it? It's intended to be a mesh administration slash monitoring tool. It's intended to serve as a protocol research tool and offer some sort of node simulation. Now the intention is basically to be able to talk to each one of the developed mesh protocols and offer some sort of common visualization and data aggregation to all of the different protocols. So what is it not? It's not intended to be like a light node run topology tool that each of the node runs, and it's intended to be used by actually the developers and not the end users that are running the nodes. So these are the main features that I was still aiming at, and the implementation degree on each one of them varies. So the first is the ability basically to aggregate topology information from as many different mesh protocols as possible. And it was a bit, there's some JIT inspiration that took place. The idea is basically to continuously apply small net differentiated net diffs to some network module that the model that the tool maintains, basically to be able to record those differentiation packets over time, and later on possibly play them back and show how the topology changes over time. Additionally, it offers administration tools that some of which actually leverages existing Eclipse remote administration tools like file system mount and well, all sorts of DNS service discovery is another example. So this is basically a lot of functionality that already exists in the Eclipse platform, and we're unable to basically leverage that and apply it to node mesh node administration. And that includes the batch node operations is somewhat of a more envisioned functionality. It doesn't yet exist. So that will hopefully allow administrators to batch apply firmware updates, package installations, and basically compare the package installation status between different nodes and other things like that. Another functionality that's been incorporated is the GIS database. The tool is running basically H2 embedded database in memory, and on top of that I applied some GIS functionality. So this allows well, it's basically a topology independent query system. So if you have GPS information of your nodes, you basically be able to query the network based on regions, areas, and not the actual routing state that each one maintains. So that might even offer later on additional features. So service discovery, I mentioned, is something that already exists in Eclipse, and we'll be able to use that. Visualization tools is also something that I'm aiming at, but it will probably require more manpower. But yeah, everything that relates to visualizing how the current state of the network is, like applying heat maps of links, all sorts of visualization tools that basically allow a better insight into the current state of the routing protocols. And monitoring is another feature that might later be incorporated. It's not. So I'll show a video of the quality, what might be less than perfect. Okay, so this is basically a video demonstration of some. I'll show it. It's basically a tool in action, and what we can see here is the map, which is based on OpenStreetMap. What you've got here is a GPS-enabled node that is simulated to be running through the Berlin metropolitan area. These nodes, I'll just pause this for a second, are static nodes that were derived from one of the data sources that are currently supported. So it's just an XML static fry-func map information. And later on, we'll be able to see. Okay, so I'll just mention another thing. The tool can actually talk to a Kismet sniffing tool. So what we're seeing now is that actually nodes being discovered as whatever war driving is taking place, and these are the nodes that are picked up by Kismet and displayed on top of the network as well. So the Kismet support is just another data source that the tool is currently able to talk with. And okay, so I'm just going to finish. So this movie is a bit outdated. I'll just so a few words about the architecture of the whole tool. So as I mentioned, it's Eclipse-based. So Eclipse has something that's called OSGI, perhaps some of you know it. It's the Eclipse way of saying a package management system. So I was able to build on top of that, and it allows very good modularity of the code. So let's say if any one of you guys would like to offer a data source plugin for the tool, it would be really easy because you basically only have to implement or copy one of the existing plugins, adapt it to your topology update mechanism, and basically offer it as a plugin to the tool. Another framework that was used was EMF, which is the Eclipse modeling framework, and that allows a lot of the code. Well, currently I'm the only one that is working on it. So the EMF offers a lot of code generation functionality, and it's basically just enables you to put up much more code single-handedly. Okay, so the data layer, as I mentioned, is H2 backed, the H2 database engine, and it's currently running in memory, but exporting the data to other databases should be relatively straightforward. Okay, now the UI layer currently uses something that's called GEF. It's also an Eclipse framework. It's called the Graphical Editing Framework. And everything 2D in the map is basically built on top of that. And something else that I just started to work on is the integration with the NASA Whirlwind project. So maybe I'll just show. Okay, so this is a more recent screenshot of the tool, and what we can see here, or can see, depending on where you're sitting, is the network model over here. So we can see the different data sources. We got XML, OLSRD, ISNet, and the tile layer. They're all listed on the data sources model. Over here we have the 2D map, which is basically OpenStreetMap drive, or any tile server basically you can plug in. And on the third pane you have something that's really experimental, but that's the direction the tool is going. It's basically to leverage GL enhanced hardware acceleration to display the networks. So hopefully everything will transition over to the NASA Whirlwind tool. And on the lower pane, what we can see is the H2 database that allows you basically to execute node queries basically while the tool is running. So you can any SQL queries, node queries you'd like to execute, you do here, as well as GIS enabled queries, like based on geographical features. You really execute them. Okay, so one of the main issues, 1 minute. Okay. So one of the main issues I had to deal with is basically that each of the different protocol implementations uses a different database scheme. And I'm not sure if any of the guys running this particular website are present, but this is the Open Networks Interoperability project, which aims to derive some sort of a generic database schema so that each of the networks could actually swap information more easily. So, well, this schema doesn't yet exist, and it would be a great thing if this conference would actually be able to produce such a schema. But so, from the Mestral perspective, I currently use a very simple schema, which should be extended based on whatever is decided, like to be a good, common, generic node schema. Okay. And so roadmap includes VATNet support, Babel support, hopefully to be able to run 1K and then 10K node networks comfortably without too much resource strain. And another feature that might spring up is to be able to use the GPS aggregated data as a backup to the actual satellite data. So let's say that I have an existing network and I already know the positions of, let's say, all the nodes. Once a new node comes into the network, I should be able to triangulate its new position based on existing data. This is actually what Google and Apple have been doing with all the information they've been collecting. When you fire up your cell phone, they're using existing data to map your new position. So we might be able to do that with this database that we set up. And that's it. So if you got some questions in 10 seconds.
There is an ongoing project which is sort of paused with me and Rita over years. Is also the really need for having common node database schema.
Yeah, so that's urgent actually. Yeah. Just one last point, which is really important, that if anybody is interested in coming and working on the tool, helping out, because it's currently in alpha stage, so that would be great actually.
I have a question. Do you know FrameUp?
Yeah, I mentioned the tool was derived initially from 2009 from FrameUp, and it's pretty much, it's a long way from where it started.
But there is a main difference.
Well, I wouldn't know where to start. Well, let's say that in terms of being able to talk to multiple data sources, that's a similarity that still exists. But the whole transition to Eclipse, plugin system, EMF, the UI is totally different. I mean, basically the whole adaptation to EMF and GMF, the two Eclipse frameworks, have really introduced a lot of the differences from the original. Okay, thank you. What?
Maybe make a cut here.
Yeah, thank you very much.
Okay. Hi. I'm and I'm here with my colleague Martin. We're both from the Department of Electronic Systems. Louder. That's right. We're both from the Department of Electronic Systems at Aalborg University in Denmark. I'm going to talk just a little bit about network coding in wireless mesh networks. Martin and I are currently working on a master thesis about network coding in mesh networks, and we started out just a bit inspired by something called CODE, which is a project from the MIT Computer Science and AI Lab. We think we can avoid some of the overhead of this CODE project by having a closer integration with the routing protocol we were able to use back in advance. We would like to have a performance evaluation of this network coding in a real wireless mesh network, which is compared to some of the other evaluations of network coding in mesh networks. They are usually just theoretical or simulated. And the working type we have right now is cat only. Short for coding applies to wireless on mobile networks. Just to short disclaimer, we're still in the very early phases of this project. We don't have any results to show you, any graphs. We don't even have a complete concept of design of this system. But what we would like is just to put out the idea, have maybe some feedback and some comments from some of the experienced developers that are here. We call it a lightning discussion because this is a lightning talk. Just to sort of describe the basic principle behind network coding, it is that in wireless network, instead of having the nodes simply forward packets, we allow them to combine packets and actually process them. So the simplest explanation that we can do is that if a node receives like the XOR of two packets, and it already knows here, packet 1 and 2, and it already knows the content of packet 2, it can extract packet 1 from these two packets. And we can of course switch packet 1 and 2 to extract the other. If we should look a little bit about it in a topology setting, if you imagine a network with just 3 nodes, A, R, and B, and the nodes A and B communicate through a common relay node in the middle, and you want to have a node A transmit packet 1 all the way to node B, and node B will transmit packet 2 all the way to node A. Without network coding, this requires 4 transmissions, as shown on this figure. If we allow the relay node to combine these packets, we can actually manage with just 3 transmissions. Of course, it requires the relay node to know that packet 1 has stored, node A has stored packet 1 and node B has stored packet 2. And then the relay node can simply XOR these 2 packets together, and node A and B can extract the original packet or the missing packets from this combined packet. The previous example required that the nodes each store the packets that they transmit, but in a wireless mesh network, you often have the possibility to overhear the packets transmitted by other nodes, so we can actually exploit that as well in this setting. So if we consider this X topology, it's just an extended example from the previous topology, where we have nodes A transmitting packet 1 to node B, and node B transmitting packet 1 to node C, again through this relay node. But this time, node C can overhear the transmissions from A, and node B can overhear the transmissions from node B. We can again manage to transmit the complete both packets with just 3 transmissions instead of 4 otherwise required. We can extend this principle to some topologies that are very nice from a theoretical point of view, but we may never experience in a real setting like this one, and you can of course add multiple crossing flows to this topology. So our idea is to just start out with this simple Alice and Bob topology, this X topology, and try to use information already present in background about the surrounding nodes. That will transmit these originator messages or OGMs. So if node A will transmit this OGM, it will be received by node R, and node C, and node C will then forward it again to node R. Will decrease this TTL value, the time to live value, by 1. So we can, from R, deduct that node C can hear node A, and we have what is basically a coding opportunity. As I said in the beginning, we're not very far into this, so there's a lot of questions. The basic question is simply when to code. If you have packet losses on the links and you lose the packet, which is the combined packet, you are actually breaking more than you actually break like 2 different transmissions at once instead of just one by losing 1 packet. What do we do about wired links, where you can't overhear the transmissions? This sometimes makes sense to hold back a packet and wait for a coding opportunity to arise. That's another question. Because the wireless nodes need to overhear the other transmission, they should be in promiscuous mode. That means we have to process all packets in the kernel module. So there's a computational overhead there. There's also some storage requirements that we need, because we need to store both the overhead packets and the packets we transmit ourselves, and the list goes on. So we will try try to answer some of these questions in the coming months, and hopefully we will turn to the next Batman mesh and have a Batman module with just a knob you turn on, and we turn on this network coding, and let's see if it works.
So if you get a packet that is like packet 1 XOR packet 2, how do you know that it's packet 1 XOR packet 2 and not just some random data anchor?
Yeah, you will have to append a coded message header.
Louder.
Louder. Append a coded message header to a new Batman packet, and which will just state that this is packet 1 and 2 from the
Yes, we're currently working with the custom Batman packet header, telling you this is a coded packet, including these two packets.
So the idea is only for compression and not only that you will send this new bandwidth to get because your compression.
Could you speak up, please?
Okay, so I'm asking if the idea is only to compress things or also to add some new values to this free space you get because of, for example, because of decoding, you can also have some checksum or correction codes also. That you will be able to correct.
There's no error correction in this idea.
So yeah, but have you thought about this? So that you could add maybe some error correction in to make for, because this is really bad if there's a loss in it. Because, so, but maybe we do this and add error correction, then it's maybe better for loss links because it would reconstruct this packet. So maybe there should be some trade-off with these two approaches, which would make it then at the end no compression because it would be, but you would this 1/4 of the free space used for error correction. So that there will be the same bandwidth input, but you will get better performance in the loss links, which I believe is quite often in the wireless.
One could choose to transmit the same coded packet twice. It does not save. Then we do not save any airtime, but we get a higher throughput level. So there's a packet loss.
I was under the impression that network coding is more sort of in the IEEE fields, directly on the like the MAC layer directly, or directly on the cards. Or is that what the literature will say about network coding? Is it really on that routing protocol level, or is it actually below?
It can also be in the application layer. Just for peer-to-peer networks, if you have a file that you cut out into chunks, it does.
Okay, so that's totally independent.
Yeah.
Okay. And the other question is, wouldn't that introduce more buffer load as we learned before?
Yes.
The same. We have just a lot of buffer bloat. If buffer bloat exists, it mostly exists in situations where we have not enough bandwidth to transmit stuff, so the buffer is already there where we accumulate packages. When buffer is empty, then we most likely have enough airtime to transmit it anyways. So maybe it would be, especially in kernel space, an option instead of building our own buffer for this, just using the transmit queue of the system itself.
Yeah, and sometimes we have the possibility to remove 2 packets from the transmit queue at once by just combining them and transmitting that as well. So we actually emptying or have the possibility of emptying the queue faster. This only makes sense if you have a congested network. If you don't have any packets, other packets to combine.
If you don't have a congested network, you don't need to save airtime with network coding.
So could you give an idea of the time constants involved? So for example, how long are you going to retain old packets so you can XOR with them? Are we speaking milliseconds, seconds, hours, years? Just a rough idea.
I will explain more than milliseconds. So,
Milliseconds.
The only thing you maybe didn't mention, but you have to keep in mind, is that when you base the functionality on overhearing, and when you want to do one single transmission of 2 packets that are XOR to save airtime, but then you have to make sure that both links can work on the same transmission rate. Because usually, IEEE 802.11 these different multiple rates, you know, and it is not always that you have your anchor in the front and the one on the back at the same rate. But if you want to exploit that, then you need to be in that situation. So,
and the whole retransmission in the Mac layer doesn't work as well because we're actually targeting two nodes at once with one packet.
Yeah.
So we have to basically choose randomly between two nodes.
So, okay, let's say you have that situation where C over here is a packet that is intended, that's sent from A to D, right? Okay, so R has to know that C has overheard A's packet and that B has overheard B's packet, is that right?
Yeah. Or at least with some probability know that C will overhear transmission from A.
How would it, like, so how do you get that information?
From these OGM messages. So they are broadcasted around the network or in this OGM message on this link as well, the TTL of one is less than the other one, we know it has been followed sometimes.
I understand that your work is an academic work, right? So it's not the first time I hear this idea, so you should have seen the previous work on this stuff, right? For example, in Italy, I heard a PhD student who is doing exactly the same stuff. Maybe it's not exactly the same. I don't know if you have looked at the literature on this network coding at this level.
Maybe we cut the questions here and we discuss after, so we can proceed with the next talk. Yeah. Okay, thank you. Yeah.